In this lecture, we will discuss a few more TRIZ principles. We will also discuss some research and development work which are in line with these principles. TRIZ principle 24 basically says intermediary, and it might seem rather obscure, and what relevance does it possibly have to chemical technology? But really you can look at it from the definition that intermediary is really a go-between. And so in that sense, for example, they say that intermediary could be something like a nail set is an intermediary, and or you can look at another where you're effectively temporarily merging one object with another. And so for example, you have to carry some hot pans and pots from the kitchen to the dining table, and you need some kind of a pot holder to hold it. Or it could be a case where for example, one has to record an ECG, and you know that they have to put those electrodes on our body in the chest and legs, and the way those are put, those electrodes, is with the help of a suction pad. And so the suction pad in that sense is a go-between the electrode and the body, and the moment the job is done, you just take off the suction pad. And so that again is a definition of intermediary. Okay. Now, if you were to look at it from a chemical technology perspective, I was just thinking that maybe it's not a bad idea to think of intermediate as synonymous with intermediary. And intermediates are something that are very, very common in chemical technology. Okay, so let us look at a modified version of principle 24, where in fact, instead of calling it intermediary, we are calling it as intermediate. And the two aspects that we will look at are intermediate as product and intermediate focused process. Now, I've of course mentioned over here that these are not there in the original TRIZ definitions of intermediary, and this is just an inclusion made by the course instructor. But I do believe that there is some relationship between intermediary and intermediate. Now, so if we look at intermediate as a product, and we will of course discuss the more detailed work that was done under these as we go along, but the three things that we will look at, one is how the intermediate itself, which earlier used to give us a particular raw material or a product or a reagent, instead of that itself can be used as a product. Okay, and I've given the example of low sodium salt, which is a mixture of sodium chloride and potassium chloride, and we will see how it was beneficial in using the intermediate itself as a product. The second is what I referred to as green bromine. It's really a mixture of bromide and bromate salts, and here again it has a very beneficial effect. It can be obtained as an intermediate in some processes through which bromine is manufactured, but the intermediate itself can be used as a reagent rather than utilizing it for production of bromine. So that again would be something of interest, and we will discuss it here. A third thing which we will discuss when we discuss iodized salt, but I've mentioned it here, is latent iodine, which is again a formulation of iodide and iodate salts. Now, usually one of these is used as an iodizing agent. It's either potassium iodide or potassium iodate, but there is an opportunity to use the intermediate itself as the iodizing agent, and it greatly simplifies the process by which the iodizing agent is produced. So I put it here, but we will discuss it when we are discussing iodized salt. Now, in terms of process, well, you see, an intermediate is processed to finally get a product. But the focus has been excessively on the product and not so much on the intermediate. But one could look at changes in the sequence of processing, keeping the intermediate and product in mind and their applications, and see how one can innovate around the process and basically with the emphasis on the intermediate. So we will discuss one example where the production of magnesia, MgO, can be made a bit easier by really changing the sequence in which we do things, and where we really put the emphasis on the intermediate and an alternative way of processing it. The second is again related, and it links up a product with the intermediate. There is a particular form of magnesium hydroxide which is used as a compatibilizer for incorporation in polymer, and that compatibilizer usually is basically coated on the magnesium hydroxide after the final product is obtained. But if we were to do the coating intermediate itself, you could actually end up getting even more beneficial effects, and that's the kind of thing that I will discuss over here. So I hope you can see how we are trying to look at intermediate as a product and intermediate focused process, and I must also link it up with sequence changes, which are also very critical to this whole approach when it comes to the process.
Let me tell you, as chemical engineers, as chemical technologists, these are opportunities which will come your way all the time. It is for you to see the opportunity. So let me take you through one. You see, at that time, we spent a lot of effort in making magnesium hydroxide. Why? Because magnesium hydroxide you can calcine to MgO, and all these refractory linings, they have MgO. Either MgO or zirconia, but zirconia is much costlier. So for most applications, MgO suffices. So steel manufacture, etc., you'll use the furnace lining as a refractory material like MgO, which has a very, very high temperature before it decomposes. Now, problem was that to make magnesium hydroxide, what we were doing was that we were taking the magnesium chloride, which was there in bittern. That's how we got interested. And we were adding lime to it. Why lime? Because lime is the cheapest. So we were making magnesium hydroxide. You can add sodium hydroxide also if you want. But it's not going to be very helpful because it's much costlier. Okay. Or alternatively, you can add sodium carbonate, soda ash, convert it into magnesium carbonate, and then calcine the magnesium carbonate, and you'll get MgO. So we were using lime. Problem was that when we were using lime, the reaction mass was very slimy, and it was extremely difficult to filter it, and to remove all the impurities from the magnesium hydroxide before we could calcine it. So we had to keep on washing, wash, and get rid of everything, and then get it pure enough and then calcine it. But it was a tedious process. Now, a thought came to me. Suppose I'm adding lime into magnesium chloride. What will I get? I'll get magnesium hydroxide plus calcium chloride. So I do a coarse filtration. First, I get rid of most of the liquid, and I have this. And the idea was that what happens if I change the sequence and first calcine this crude mass and then try and remove the rest of the impurities? Why? Because whereas magnesium hydroxide is very slimy and difficult to filter, MgO is much easier to filter. MgO is not a slimy material. So when we calcined, we ended up actually getting MgO plus calcium chloride. Now, if you add water to it, you can take out the calcium chloride without any problem of filtration. Not only that, because the reaction of anhydrous calcium chloride with water is extremely exothermic. So what happens is, even if I start with big mounds of material, The moment it is in contact with water, because of that heat, there's almost like a miniature explosion, and the whole mass, that boulder type of materials, they just fall apart and become a very nice powder. And so you can wash it off cleanly, and you end up getting a very pure MgO. You can see it was novel enough that these are all patented. And just to show you, this is the crude mass which has got magnesium hydroxide, calcium chloride, maybe some unreacted lime also, I don't know. And when we calcined and washed it, we ended up making the purest product you can imagine in an extremely simple way. How did we do that? We changed the sequence.
And of course, we focused on the intermediate.
Take another case, again related. You can use magnesium hydroxide either to make MgO, or magnesium hydroxide is also used as a fire retardant. In a lot of things where there is a fear of heat development, cables, and things like that. So, typically, what people do is, because MgOH twice is not directly compatible with the plastics, it is too hydrophilic. So, the Japanese found a way of putting stearic acid on the magnesium hydroxide, coating it, and made it hydrophobic. And that really happens because of the acid base reaction between the magnesium hydroxide, which is basic, and stearic acid, which is acidic. So it forms a coating, and then it becomes easier to incorporate it uniformly in plastics. What we said is that what happens if we add stearic acid to a magnesium hydroxide slurry before we have done the complete filtration and washing. So we put that, and it again went and sat on the magnesium hydroxide, made it hydrophobic, and it became very easy after that to filter off the magnesium hydroxide, and we did not have this slimy mass. Effectively, we were able to increase the filtration rate by almost a factor of 3, and we were also able to reduce the moisture content by 15%. So it was a huge benefit, and merely by changing the sequence. Why only make the product pure product and then coat it with stearic acid? Why not try to incorporate the stearic acid at the time of filtration to gain an extra advantage? Most of the magnesium hydroxide goes into formation of MgO, but we realize that when we calcine magnesium hydroxide to form MgO, that small amount of stearic acid which we had incorporated will burn off as CO2. And so now I'll get an MgO which does not have any trace of stearic acid, because in those applications you don't want stearic acid to be there. So, depending on the application, you can tailor make things. Let me show you one where intermediate was used as product. I come back to this. What did I tell you? That after making salt, if you keep evaporating the bittern, after removing sulfate, it forms what is known as a double salt crude carnallite, KCl MgCl2 3H2O, and along with that, all the NaCl that is present in the bittern also precipitates out. So you get a mixture of this. When you decompose this by contacting in water, you know, you get a mixture of KCl and NaCl. Now, everybody has been focused on trying to recover KCl from this by making pure KCl for fertilizer or whatever. Now, we were at that time working with Unilever, and what happened was that Unilever were interested in low sodium salt. ACL, NaCl is what is known as low sodium salt. NaCl raises blood pressure. KCl tends to lower it. In fact, just last night I had to do my mother's sodium potassium balance, and so at that time I thought that let me put this example in. Now, what people have been doing up till now when they're making low sodium salt is they take pure KCl and they buy pure NaCl and they blend the two and they make NaCl KCl. Now, what we said is why not use this intermediate itself as low sodium salt? You know, why should I even do this? And what that did is that it crashed the price of production of low sodium salt, and that's the technology that was licensed to Unilever. I don't know if they are still practicing it, but at that time they told me that in all the North soup, etc., they were actually using low sodium salt. And so there might be a little bit of this technology in every time you have some North soup. Take another example. This is a paper published in 1925 in Journal of the American Chemical Society. These people were from Yale University, and what they had done was that they were able to do bromination reactions without using liquid bromine, but instead what they did was they could, for example, either take 5 is to 1 kbr kbro3. You know that upon acidification it will convert back into bromine. Or if you change the ratio to something like 2 is to 1, what you can do is you can do substitution reactions with almost quantitative stoichiometry of usage of bromine. Normally, you know that if I use Br2 and I try to do a reaction where I do an aromatic substitution to put in a bromine atom into an aromatic ring, half of it becomes HBr. So your bromine atom efficiency is about 50%. Whereas with this, you'll get 100% bromine atom efficiency. What was interesting is that when we were looking at how bromine is made, one of the processes is what is known as the air blowing process. What you do is you first take your bittern, let's say, which has bromide, okay, and you pass chlorine into it under acidic conditions. The chlorine oxidizes bromide to bromine and itself becomes chloride. So you get bromine out of it. In the cold process, what then is done is that this bromine is trapped in alkali. So here you can see NaOH, and you end up making 5 is to 1 sodium bromide, sodium bromide. If you reacidify this, you'll get bromine, and then you can distill that bromine and you'll get pure liquid bromine. That's the standard process. What we did is that we took this, we could either use this mixture or we continued oxidizing it further and converted into this 2 is to 1 bromide to bromate, which is what Hill and Francis had done. What was the difference? Hill and Francis had taken pure KBr and pure KBrO3, and then they had mixed it. Obviously, it would be a much costlier product. Whereas here, we are getting the product itself in a mixed state. There is, of course, some amount of sodium chloride which is present, but we found that in most of the reactions, the sodium chloride does not interfere with the bromination reaction. And ultimately, therefore, we were able to get a very nice solid reagent which could be used for bromination. All you have to do is take your organic compound, take this, add acid, it will regenerate either Br2 or it will regenerate HOBr, which is used as a brominating agent. And we could cut off liquid bromine from the product life cycle.
Tetrabromobisphenol A was the first molecule that was synthesized from bisphenol A using the reagent that was obtained directly in the mixed state, the 2 is to 1 reagent.
When industries tried it out, this is great. It works fine. It was tested by Merck, tested by TRIZ, Arcolab, many other companies.
Copying is another important TRIZ principle, and in fact you can see what is meant by copying. But then I was just thinking that there could also be other things that one can consider as part of this, and that could be just copying good ideas. And for example, you could have a problem and someone has done something related in the prior art, or it could even be you or that who has done something, and maybe you could think of copying your own idea in a different context. So for example, of course these are maybe euphemistically, you could think of things like let's say what we call drawing inspiration. It's actually a form of copying, or expanding the scope of something. That's also a form of copying, or sort of moving knowledge across boundaries. Again, I mean, obviously for different applications, but in a sense, all of those would also be forms of copying. In fact, although we discussed the bromide-bromide couple in the context of intermediate, and that's because we really produced it from the intermediate, but at the same time, considering that the inspiration came from the work of Francis and Hill, very old paper in Journal of the American Chemical Society. In that sense, really, one could also view it as an example of copying. Similarly, we found many other applications of this reagent going well beyond the work done with tetrabromobisphenol A, which was an aromatic substitution reaction. We went to other kinds of bromination, but in a sense, they were all copying from the original work that we did with tetrabromobisphenol A, and the work that was done for us by Professor D. Basavaya, where he showed that it's a very promising reagent for example, benzylic bromination reaction.
The general idea of copying should be used more broadly. Just to show you how when you come up with an idea, like we were very fortunate to come up with, and then how we could apply that same thing in so many areas. I'm actually talking about things which were extremely important for technology development. One of my colleagues, Dr. Ramachandraya, and a few others had done some initial work where we made this para-nitrobenzyl bromide. So you start with nitrotoluene and you do a benzylic bromination. Okay, CH2Br. A lot of good work was done, and we were able to develop a technology, license it to a company, started manufacturing this, and the importance was that this compound is actually used in beta-lactam synthesis. It's a protecting group. We basically acquired the skill to do benzylic bromination. Now, once you have that, and this will be true about all of you, you will come up with invariably some very bright thing. It need not be necessarily a synthetic protocol. It could be a software. It could be something which you develop. Once you do that, you should be obsessed with what you have done. Okay? All the time, it should be in your head. And of course, I mean, that's the kind of obsession that maybe my colleagues and I had. The second, for me, it was a big advantage because I was the director of the institute. So I knew all the disciplines. So what happens is that you know what are the problems, and you can always say, where does this fit into the scheme of things? Okay, it may not fit. I'm not talking about a force fit, okay? But it actually worked out that we had an excellent fit. There's an anion exchange membrane, okay, which was being made. In fact, our institute developed the technology in 1968. It's based on what is known as an interpolymer. Okay, so that was well known. The problem was that it involved the introduction of a CH2Cl group via chloromethylation. It was a very good technology at that time. Problem was that chloromethyl ether is a dangerous chemical. People don't want to use it. I used to hear for about 15 years, oh, we have made a fantastic membrane, it's great stuff, but we don't want to make it. I said, come on, I mean, how long are we going to play this game? Either you decide that, no, we are going to abandon it and move on. Right? But this business of every time you'll show a promise and then you'll back out. So I realized this can't go on. You see, all the time, everybody was thinking that I must necessarily put in a CH2Cl group on the aromatic ring directly. Why do you do that? Because after that it's reacted with trimethylamine to quaternize it. So I said, at the end, what do we want? We want just a CH2X group of the aromatic ring. I don't care how it's made. So, I said, why benzene? What happens if I start with a toluene equivalent? So, methyl styrene. So, I said, why not just do a polymerization of methyl styrene and divinyl benzene? And then you try your benzylic bromination. So, the idea was really we wanted to apply this technology in a much broader way. And it was just too good. I mean, we could brominate it, we could make, honestly, the best membrane anywhere in the world. It was that good. So all our new technology is all based on that. So it was as simple as that. Okay. And in fact, I had a person who was heading the membrane group. He had come to us from Solvay. Solvay polymer. So he understood how important it is, really pushed it finally, and it's all been granted patents and things like that. So we know that it was a new technology. I showed you about losartan. First step where you connect the imidazole ring to a side chain, okay, is basically done using para-bromobenzyl bromide. Not very different from para-nitrobenzyl bromide, except that one is bromo and one is nitro. Just played the same game. In fact, there was a home paper about 3 years back, which people did, and they did a great job of this. And when you think that, yeah, more or less I've reached the limit, what happened was I happened to be in the Technology Council of Asian Paints. So then what happened was I found everybody talking about how the cost of making alkyd resin, which is what these are reactive resins, okay, how it's gone up because the cost of unsaturated oil has gone up enormously. I said, why can't we use that same trick? We had actually played that trick before. We'd also shown that even if you take a saturated molecule, like just a paraffin, okay, that you can actually do a bromination there. It doesn't need to be an activated hydrogen. And it ended up that we made just like linseed oil. Okay, from what? From something like palm oil. Okay, I mean with zero unsaturation. Which you would have thought next to impossible. Now, how did we do that? We did a bromination and then we did a dehydrobromination. Okay, I don't think it's going to be practical. When I look at the cost, somehow it doesn't look that attractive to me right now. But you never know because these things, you've seen what happens to petrol, diesel price, etc. I mean, at a future date, you never know. It can become quite an interesting, promising technology. I mean, you can just see that same thing was used across the board in so many different areas, and there's no relationship among any of these areas except for the fact that they all involve a bromination, a radical bromination. I would say that is our principle of copy, in our case.
I told you that if you react magnesium chloride with calcium hydroxide lime, you get magnesium hydroxide and calcium chloride. Always, whenever you make a magnesium hydroxide from lime, the amount of impurities that you get are invariably much higher. Of course, some of our innovations improved it, but still, it's very difficult to get purities beyond something like 96-97% practically. Whereas there are many applications where the MgO, like in a steel furnace, needs to be much purer. You need to be at about 99%. Now, at that time, what we thought is, Ammonia is also a base, and again, that was not new. That magnesium chloride can react with ammonia, means ammonium hydroxide, and it will form magnesium hydroxide. Now, in that case, all you get as a byproduct is a soluble impurity, which is ammonium chloride. Much easier to wash off. So then, we did that. Problem was, just like in the solvay process, you see, solvay process, you are turning over the ammonia, isn't it? Otherwise, solvay process would be way too costly if you did not regenerate ammonia. So we drew inspiration from the solvay process and said, we have got the same thing. We are getting ammonium chloride from the reaction of magnesium chloride with ammonia. So why don't we, again, just like Mr. Solvay had done, we regenerate ammonia and we'll be left with calcium chloride. So what did we do effectively? We we did the reaction with lime, but we did it in a contactless method. Means we first contacted it with ammonia and only regenerated ammonium chloride with lime. So effectively, the net stoichiometry is still magnesium chloride plus calcium hydroxide, giving you magnesium hydroxide plus calcium chloride, but it is done indirectly. And because of that, we were able to make a super pure magnesia. And just to give you an idea, this is the magnesia that we could make through this contactless process. And this is the magnesia which we were getting earlier. And when it was evaluated, what they basically said is that this stuff is now suitable for primary steel making. You know, and all you can see is that we've shifted knowledge across boundaries. That's it. Okay, and nothing more than that. So let me take you through another example of shifting knowledge across a boundary. And you saw how BASF learned from the contact process and shifted the knowledge to the ammonia process. It's a case of shifting knowledge across boundaries. Now, let me tell you another. In fact, the patent for that was granted just about 2 months ago, 18 Jan 2021. So let me tell you how we move knowledge across boundaries. And this is the work that was done with a company called Rubermin, okay, and done by some of our masters students who were working there. What they do is that they recover metal value from spent petroleum catalysts. That's what they do. One of the processes which they use, the first thing is that they have to roast the spent catalyst to burn off all organics. And then they basically do hydrometallurgy and extract out selectively things like nickel, molybdenum, cobalt, etc. Now, what happened was that when they were doing this, there was a lot of sulfur compounds which were also there in the spent catalyst, so that when they were roasting, their roasting temperature was about 650 degree or 700 degree, 650 I think, or so, that they were generating flue gas with a fairly high amount of SOx, SO2 and SO3. And because I was a consultant for them, they had raised this issue that they're spending too much of money for to scrub out these SO2 and SO3. And they were using at that time sodium hydroxide solution and passing the flue gas through it. And basically, this stuff would come out. And also, of course, flue gas will have carbon dioxide. So it will form sodium sulfide, sodium sulfate, and sodium carbonate. But as more and more SO2 comes, the sodium carbonate will gradually get all converted into sodium sulfate or sodium sulfide, and the CO2 will subsequently escape. The moment I saw SO2 and SO3, obviously my mind went to what? Contact process. And I said, what do we do in the contact process? We do an absorption, okay, the double contact, double absorption process, where what we do is we take the SO2 and SO3 and pass it into sulfuric acid, and it becomes like oleum. And because why? Because SO3 is very strongly soluble in sulfuric acid. It will form more sulfuric acid. Okay. But SO2 does not have high solubility in sulfuric acid. So that's how you regenerate pure SO2 from SO3 and continue with your contact process. So we said by doing this, we will be not only able to remove the SO3, we'll also get sulfuric acid, which is required in the process, and it reduces greatly the amount of alkali that you require to subsequently scrub the SO2. We were forming something like a 40-60 ratio of SO2 to SO3. So there was a huge reduction in the usage of alkali. And you also got sulfuric acid, which you could reuse in your process. So what did we do? We moved knowledge of the contact process into what? Into flue gas. Let me now take you to another example, which is porous materials. Okay, this is number 31 in the among the 40 principles. The reason why I thought I will show you this is that sometimes some of you might think that what work should I do after I'm gone from here, and let's say I have to do some research, and suppose I tell you go work on porous materials. You'll say, what porous material? What do I do with porous materials? So let us see what the principle says, and I'll show you an extension to into many other applications. So make an object porous or add porous elements. Okay. So drill holes in a structure. Who did that? Bosch. You remember? He drilled hole in their reactor to allow the hydrogen to pass through. Or I could drill holes to reduce the weight. So there could be various reasons why you might want to incorporate porosity into a solid or a liquid. We also know that there are many very porous substances which are being looked at as, like, for example, a sponge to mop up hydrogen. And so when people are thinking of using hydrogen gas and running vehicles instead of an electric vehicle, they want to run it in a fuel cell with hydrogen. You could actually take a sponge, like a palladium sponge, and it mops up very large amounts of hydrogen. So instead of carting around hydrogen in a cylinder, you can actually absorb the hydrogen on a palladium sponge and then use it in the solid state. So that's, let's say, various applications of porosity. Or, for example, when people do soldering, they use a porous mesh and they basically mop up the excess wick.
Okay. But I found that these guys were struggling for examples. This told me that they hadn't thought through it. Okay? So I just thought a bit more deeply. Okay? And so I came up with this list, okay, of all the things that I've encountered. Okay? You remember I talked to you all about explosive, the ammonium nitrate oil, how you emulsify one in another. But the thing is that unless you introduce some voids, even if you have the right fuel and oxidizer composition, it will never detonate. And that detonation process, when you start looking at it, how you create shock waves, and then how there's a collapse of these bubbles and it generates huge temperatures, and that's what actually triggers the detonation. I know how important it was, okay, for us to control the size of the voids in the explosives. Okay? You can control it by also introducing things like glass microballoons, but that's prohibitively costly. Who wants to pay for air? At the end of it, okay. So we thought, let's do it with just air, and so that was the control. Of course, soak up liquids or gases in porous materials, sponge action. Okay? In fact, it's you look at a sponge. What is it? All pores. You put it and it's all going in. Now imagine, suppose you are transporting very volatile fuel, okay? And vapor pressure is very high, and suppose I soak it up, in a spongy material, or something, maybe where the voids are such that I need barely 0.1%, suppose, to soak up all the rest. Suppose I could make a material like that. Okay, then, I could transport solids in a safe way. And at the other end, I can do some jugglery and again convert it into a liquid. Okay, and sponge, how important a sponge is, you all know. Okay, Bosch's example of drilling holes in the jacket to allow hydrogen to pass through. From our own, whatever we have studied, you know how important it was. Okay, Frash process, which you had learnt in industrial engineering chemistry, how did they take out the sulfur? I mean, they used superheated steam to melt the sulfur, but sulfur is too heavy. Okay? You can't float it up. Okay? So what did they do? They introduced some surfactant, and injected air, and they frothed up the sulfur, and buoyancy lifted it up. Isn't it brilliant? You look at the examples. Okay? In fact, microporous, Gore-Tex. I mean, like when you were making your presentation on chemical engineers who changed the world. One of them was Gore. What did he do? He took Teflon and he gave a big yank. And effectively, what did he do? He generated voids in the Teflon. And so what happened? If I had a raincoat, for example, the fluorine, the tetrafluoroethylene, was helping to keep me dry, even though there was porosity. That extreme hydrophobicity never allowed, a droplet actually to go through. Okay? But the air could go through, so I didn't have a stuffy raincoat. Okay? You understood? Okay? How brilliant it was? Okay? Voids. In fact, I remember how fascinated I used to be with this when I was in, again, during my ICT days in England. At that time, they were trying to develop plastic paper. And so I said, wow, it looks so beautiful, it's just like white paper, you can write. And I said, what is it? He said, it's basically polymer and they use a lot of filler, barium sulfate. So it's a composite of barium sulfate and this, and then they basically make sheets of it. And the Bank of England was interested at the time in introducing this paper for currency, and a lot of people, for some documents, they were interested in this kind of paper. And then I asked Jacqueline Wilford. Yeah, and I asked Jacqueline that, so what else? I mean, so if I just take some barium sulfate and acrylic polymer, it'll become white? She said, no, it won't. I said, what will it look like? She said, it'll look almost transparent. I said, so how did you make it white? She said, that's the trick. Later on, I learned from her, what they were doing, almost like Gore-Tex, okay? At the time of processing, after they put in the barium sulfate and they're making the sheets, just before, while it's still a bit hot, they just stretch the thing a bit. And it creates, I had those pictures, I can't find those electron micrographs. She had given it to me. And it creates slight void in that structure. As if there's a tear between the barium sulfate and the acrylic. And that is the scattering side. It scatters light and it becomes white. Absolutely from transparent to wonderful white. Yeah? So you can see how important voids are. Now, this is another great example. You see, when you are transporting, like, let's say, fruits, okay? And do you know how fruit ripens? Any idea? What leads to it ripening? Ethylene. Okay? So, these things release ethylene. Okay? And like earlier days, people used to use calcium carbide. They used to put mangoes and all with a little bit of calcium carbide, put it in a box. Now they're banned it. Who knows whether they must be still doing it. And that's how they ripen the fruits fast, okay, by generating acetylene. Okay? So what happens is that when you're transporting, like let's say over long distances, and you don't want a buildup of ethylene, okay? So you don't realize, but these packaging have tiny pores, okay, and it allows the ethylene to escape. Can you imagine it? What a wonderful application of porosity. In fact, you don't realize the pizza boxes. What do I want? When that pizza is being delivered, you have to keep it hot and you have to prevent it from getting soggy. Now, these guys figured out, why does it get soggy? It gets soggy because of the heat, right? So there'll be steam generation. And if that steam is not being taken out from the box, okay, then it'll get soggy. Or what is ice cream? I mean, can you imagine having ice? It would be terrible, right? I mean, and what gives it this is this foam. It becomes so easy to bite into it. You can't bite into a block of ice. Okay? All right. So you can see how important the porosity in foods is. I remember there was a company, it's like Badmash, and they were selling ice cream by volume, 100 ml. Because it's all hawa. There was nothing there, there was no weight, okay, in that ice cream.
Or popcorn or murmura. You imagine chewing a grain of rice, and once it's puffed up into a murmura, it's completely different. Okay, so porosity in foods is an extremely important area. So I hope you can see how porous materials can be used in diverse applications. These are all good things induced by porosity, but porosity can also create a lot of bad problems. Like, for example, you take a writing chalk. Some chalk you'll find it breaks very easily. Why does it break? Because there is porosity inside that chalk, and those become the points of brittleness. And the higher is the size of the pore, the more easy it is for a chalk to break. Whereas if you can make a chalk without those defects of porosity, you can actually write with it without it breaking. Or bulk density is a very important specification of many products, solid products. And bulk density comes because of uncontrolled porosity, the variations. So to be able to understand that and to be able to control bulk density is vitally important. So I hope you can get a feel for all the different things that you can do with porous materials. And if you have, let's say, if you're an expert in porous materials, you know how to induce porosity, how to take out porosity, whatever, you can apply it across God knows how many applications. Okay.
Not sound good enough to become an area that you might want to do your research in? I mean, I'm just saying, but, and imagine that 40 principles, if each principle was a gold mine of that kind, I mean, the sky is the limit. You've got your PhD topic. In fact, you've got your topic for life, not just PhD topic.